Here we're going to talk about the integrated form of the rate law, which relates concentration as a function of time. The rate law we talked about before we called it the differential form of the rate law, and so that's shown on the left side of the screen here. The differential form of the rate law had rate, which we know is the change in concentration over change in time, equals K times the concentration. So we could see how the rate and the concentration were related. Now, we could also see the order in a particular reactant, and so in this equation, the reactant is first order because there's an invisible 1 exponent on the concentration. If we do the calculus operation of integration with respect to time, we get a different form of the rate law. We call this the integrated rate law because of that calculus relationship. In this form of the rate law shown on the right, we connect the concentration as a function of time. And because of math, we see that it looks a little bit different. Now we have that the natural log of concentration at a particular time divided by the initial concentration equals negative K, the rate constant, times the time. So here in this equation, we have both concentration and time. And we can use this equation to calculate the concentration of a reactant at any time. Or we could calculate the time at which we have a particular concentration. If we rearrange this equation a little bit using what we know about log rules, we can get this linear form where we have that the natural log of concentration equals negative K, the rate constant, times T, the time, plus the natural log of the initial concentration. And what we see here is that we have a linear equation, that this fits the form of y equals mx plus b. So if we were to graph the natural log of concentration at some time versus time, we would expect to see a line with a negative slope, and that slope would be negative k. Rate constants are always positive, so the slope would be negative k. Okay, and so this equation will allow us to calculate the concentration at any time, or the time where we have a particular concentration. If we broaden that, so the examples we looked at on the previous slide were both first order. If we broaden this a little bit and think about the other reaction orders, we said the most common reaction orders are 0, 1, and 2 in a particular reactant, then we can see how the differential and the integrated rate laws change. So for the differential rate law, when you go from 0 to 1 to 2, you see that it's the exponent on the concentration. But if you look at how the integrated rate laws change, you can see that they have much different forms. In the case of a zero order reaction, so we see that the exponent on A was 0, which means that the value is 1, so it kind of disappears. And so we see that the integrated form of that rate law is that concentration equals negative KT plus initial concentration. So that's the form of a line, and concentration versus time will be linear for a zero order reaction. We already talked about first order. We see that it has the natural logs in the integrated rate law, and that natural log of concentration versus time will be linear. And then finally, we can look at what the form of a second order integrated rate law would be. And we see that it has these inverses. So we have 1 over the concentration versus time, and that would be linear. And so the reason that the differential and the integrated rate laws have such different forms has to do with the calculus, the math, going from the differential form to the integrated form. We're not going to do that math in this class, but you can believe me that if you were to do those operations, that this is what you would end up with. And so the point here is that we need to choose the right integrated rate law. So the integrated rate law only applies for that particular reaction order. So we have to choose the right integrated rate law to calculate concentration or time for a reaction with a particular order. So we have to find the order first and then choose the rate law. Let's do an example. So we want to find the concentration of some reactant after 22 seconds if the initial concentration is 0.150 molar and the rate constant is 5.4 times 10 to the minus 2 inverse seconds. So what are we trying to find here? Our goal is that we're trying to find concentration at a particular time. What do we already know? We know So we know K, and we know the initial concentration. And we know the time that we want that to happen. Okay, so what connects these things? We need the integrated rate law because we want to know concentration at a particular time. But how do we decide which form of the integrated rate law to use? Well, somewhere in this problem is going to be a clue about what the order is in a particular reactant. Sometimes it just says the reaction is first order, but I'm not seeing that here. Instead, the clue here is in the units on the rate constant. The units on the rate constant vary with the different reaction orders, and it turns out that when K is in inverse time units, that means the reaction is first order. So we're going to use the first order form of the rate law. So that would be natural log of concentration at a particular time equals negative KT times the natural log of the initial concentration. All right, so let's plug in what we know. We're trying to solve for natural log of concentration at time, or for concentration at time. So we'll put in the value of the rate constant, 5.4 times 10 to the negative 2 inverse seconds, and multiply that by the time, 22 seconds, and we see that our time units match, so we don't need to do anything else there, plus the natural log of the initial concentration, 0.150 molar. All right, so if we solve that, we get that the natural log of the concentration at the time we care about, at 22 seconds, is negative 3.085. Okay, so now how do we liberate the concentration from the natural log? The inverse of natural log is exponent e. So we will raise both sides to the power of e. All right, and so then the e and the natural log, they cancel out, and we have that the concentration at time t equals 0.0457 molar. And probably we only need two significant figures there, so we'll round to 0.46 molar. All right, so now we have calculated the concentration at a particular time. We see that this concentration is less than the initial concentration. That makes sense since the reaction has happened. So the reactant is being consumed.